Our next speaker is Dr. Jianjia Ma. Dr. Jianjia Ma has received PhD and Masters of Electronic and Electrical System Engineering from Loughborough University in the UK. Okay.
Thank you. I really appreciate this opportunity to introduce one of my open source project, NNoM. It's a neural network framework that designed dedicated for microcontroller. I believe most of you already know what is microcontroller and what is tiny neural network, but in case someone who doesn't. Microcontroller is a very small computer that normally have very limited resources, like very little memory, a few kilobytes, or a few tens of kilobytes, and very low computational powers. However, the data they're facing is also normally quite simple, mostly time sequence data, come from motion sensors or just microphones. So tiny neural network is a very small network which just enough to process all these data. So what is NNoM stand for? It stands for neural network on microcontroller. It manages layer-based neural network, and it's interpreterless. It's interpreterless, so you don't have large impact on your performance during the interference. And it also uses separated back-end designs, which means you can use your optimal operator to improve your performance. The current supported one is the very famous CMSISNN. It's running on 8-bit integer, and it's compatible to C99, which is friendly for most of the microcontroller development environment. So how does NNoM works? It's very similar to other frameworks. We will first need to have a TensorFlow model. It's already trained one, and then we use a converter to convert it to a form that NNoM can recognize, which is a C header. Then we use a compiler to convert the model to an executable model. Once we have this model, we can input real-time sensor data and get whatever output we want, such as classification or regressions. So what does a NNoM models file looks like? First of all, it's a C header, and it's not a flat buffer. Means all the data is stored is in an obvious way that you can read and understand. We got the weight, a layer configuration for each layers in the model, and finally a model constructor which use NNoM construction API to link all the layers together. This file is automatically generated by the converter, so you don't need to write anything, but you can understand what is happening there. Once we have this C header file, we already have the model present in a way showing on the left-hand side, which have all the links available there. But what is missing here is the running sequence of the model. We need to ensure once the model is called to run, it need to have all the input ready for it, and also it need to have the dedicated memory for it. So the compiler's work is to find out these two things, the running order and to pre-assign the memory for all the layers. Of course, the memories are sharing between all the layers, so to minimize the memory footprint. So layers, what does a layer looks like in NNoM? If you have ever tried to build your own layers in Keras, you will be very familiar with these terms. you will need to have a layer class to store all your layer configuration, a layer method to create a layer, a build method to initialize all your resources, an output shape method to compute the output shape according to the input shape of this layer and the configuration that you set. And finally, a call method to call the backend to run. So in NNoM, we use the very similar terms, but it's in C language. So we got a structure, C structure, to store the configuration, a same layer interface to create a layer, a build method to initialize the resources and to compute the output shape, and finally a run method to call the backend to run. So for each layer in NNoM, we got a dedicated C file to store all the parameters and methods for this layer. And here are the list of the current support layer by NNoM. We got some regular layers showing on the left-hand side. You can see there's convolutional, fully connected, flattened, batch normalizations. We also have support for recurrent layer, including the LSTM and GRU. We got some activations, some pooling, and finally some merging methods which are working exactly the same as the Keras versions, which means you can merge a few layers outputs to one single data. And besides that, NNoM can also provide a very good debugging information. On the left-hand side is the log that print out during the compiling process. You can see there's the running order of all the layers, the output shape, also the memory allocations for them. On the right-hand side is the log that to evaluate the model's performance. You can see every layer's runtime is recorded, as well as the complexity and the efficiency of this layer. And finally, a memory cost of the whole model plus the framework. So the project structure is I would say is a common one. We got a port folder to store the porting file, which is a single file that allows you to do some configuration. And if you want, you can pull your memory interface. Also allows you to enable the support for CMS, ISNN to accelerate your model. Then we got the script folder for the converter, a backend folder to store all the local C operators, a cool folder which nobody cares, and a layer folders to store each individual layer file that I just mentioned in previous slides. So next I'll try to talk demos two case study to show you what a typical application of this framework. The first one is a resistant band sensor, which is my PhD's work. It can turn a regular resistant band to a sensorized one, so we can collect data out of it. We have 4 different exercises that we want to recognize. It has a very small neural network in there. It's a very simple one. You can see there's only 20K MAC. It's a convolutional base. It uses Inception structure, and it only takes 2.5 milliseconds to do the inference. And we only need to run the model every 1.5 seconds to process all our data. So the whole sensor is a very low power sensor. It can run for a month in a single charge. But before we implement this model neural network in this sensor, we try to stream the data to users' smartphone and do all the machine learning things on the user's smartphone. But later we found there's really no need to do it like this way. We can just put everything in one a Bluetooth SoC there. The second case study is an interesting one. It's actually one of the NNoM's example. It has full documents support there. All the detail you can find in the links below. It uses RNN noise principle to do the speech noise suppression. The principle is showing on the left-hand side is very simple. First, we calculate the MFCC features out of the noisy speech. Then we fit the features into the INN model. The model will output a few different gains. Each gains represent each frequency band that this band will contain whether human voice or noise. Then there's an equalizer to suppress the frequency band that contains the noise and let the frequency band that contains human voice pass. So the recurrence model is the structure is showing on the right-hand side. You can see there's very complex links between all the layers. Each layer is sharing data with previous layer or other layers. There's two outputs of this model. NNoM is fully capable of deploying this model to your microcontroller, and you can see the whole process can run in a not that high performance Cortex M4 MCU in real time. Beside that, we got a little bit some more examples. They are all trained on public domains datasets. You can just simply go there and download the dataset and train your model and have a try. Some of the example can run on PC. You don't need to have a microcontroller to just try it. So summary, NNoM is a small and handy framework. It's an alternative to big brands like TensorFlow Lite. It's open source under Apache 2.0, commercial friendly. For the next step, I will try to implement 16-bit and asymmetry operators. The final goal is to keep it small. Okay, so thank you. I'm happy to take any questions.
Thank you, Jianjia. Yes, we do have a question. Do you see obstacles to use NNoM for models trained using PyTorch rather than Keras?
It really depends on how we develop the converter. One of the advantage for NNoM is it only use a very obvious way to present its model. Once you have the converter, you quantize these weights and you output this configuration of the layers. You can see the configuration are just, you can just simply copy from Keras and copy to here. It's the same in PyTorch. Just I don't use PyTorch that much, so I developed this for converter for the TensorFlow first. So it's possible, but I don't have that much experience with PyTorch.
I see. And we have another question. If I use hardware that can fuse several layers, can NNoM help there?
Sorry, can you repeat? You mean several layers of model?
Fuse several layers. Can the NNoM help in there? And additionally, can NNoM tunnel operations?
No, terminal operations. You mean terminal operations? I don't think. Sorry, can you repeat the last question again?
So, does it allocate memories for tensors in internal memory of the hardware?
Yes, the current we got two different memory supports here. We can use static memory, which is working the same as the TensorFlow Lite micro use. You pre-allocate a big chunk of memory, and then we need to try and see if the memory fit this model. Another one is we can just simply use dynamic memory allocation from Stank.
Okay. One last question. What are the application examples that use deep learning in microarchitecture platform? And what is the average size of this network?
The size of this network, I got very limited information here. For this one, it's only 20K of Mac, which is multi accumulates multiplication. What showing here is actually the NNN noise model information. This is the case study 2. You can see there's few layers. The memory showing here is taken by the model itself. There's total memory here, which taken by the model plus the framework. So it only takes 6.5 page memory. So the complexity is 200 is 200 K Mac. I hope this answer your questions, right?
Mm-hmm. Okay, thank you for interesting talk.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.